Hello everyone. Tonight I'm just going to be going over some simple harmonic motion problems and talking about how I try to approach them as a student. So, anyways, first one we have here is a electric hair clippers, and really a lot of these problems, are sort of giving context to the math you're going to be doing. And in this case, you're told that we have electric hair clippers and you're given some numbers. And the biggest takeaway from the setup of the question is that you're told it's simple harmonic motion. And that's an important fact because that enables us to use a lot of the formulas that we learned in chapter 15. So the way to start any problem though is to first look at what the problem's asking, and part A just asks for the amplitude, right? So how do we get the amplitude? Well, usually the best technique is to look at what's given to you and see if that has a formula that relates to the amplitude. Now the numbers that are given to us is the total distance, which is a tiny amount. After all, these are hair clippers, so they're blades. If you can imagine a razor, their blades are moving ever so slightly, just a millimeter and a half. Some other information is the frequency of vibration of the blades, which 90 times per minute is really fast. And the thing is, though, that this total distance is giving you explicit description of the motion of the blades, that they move back and forth at a total distance of 15 millimeters. So you have these like blades that kind of, you can imagine like the edge of the blade here, it kind of rotates through, well, not rotates, just kind of like vibrates, pulses through a total distance of 1.5 millimeters. Which means that if we model this as a simple harmonic oscillator, at the center, right, we'd say it's at the Kelvin position 0, which means on either side it moves half that distance. It'll move, 0.75 millimeters to the right, and then swing back 0.75 millimeters to the right, sorry, left, right. And that's as far as it goes on either side, right, for a total distance of 1.5 millimeters. So the amplitude then is just half the total distance, giving you 0.75 millimeters. The maximum blade speed is what you're looking for in part B. And because it's simple harmonic motion, there's this formula that talks about wave speed. If you recall, the formula for speed can be written as a function of sine, but when the speed is maximized, the sine function has a value of 1, so the max speed then is just depending on the product between the angular frequency and the amplitude of the plates, and we're doing an absolute value sign since we're just looking for the speed, not the velocity. Anyways, we know our frequency, so we know that, with them we can always know our angular frequency. There's a relationship, right, that omega is equal to 2 pi f, and the amplitude we found that in the last question, so 0.75 millimeters. At this point, you just have to go ahead and plug in what you know. So you should get an answer of about 0.42 meters per second. And finally, for part C, whether you get the maximum blade acceleration or simple harmonic motion, there's a similar formula which gives you the maximum acceleration is the frequency squared times the amplitude. So you know both these numbers and you end up with actually a pretty fast acceleration. But again, it's only at one point in time at max amplitude. So the reason why it's so high is because you have a clippers with blades that are moving over, 1.5 millimeters, and you're doing so 90 times per second, so you're pretty fast. So that's it for this question. Next question coming up gives us a block attached to a spring constant, some numbers, some position, and we're asked to find the amplitude of the oscillations. Well, so that's part A, right? You're looking for amplitude. So first step should be is to note what we have in the question and how that can help us. We know the mass of the block. We know the spring constant. So there's a few things we can already do knowing those two things. And what else do we know? We know we have some initial conditions. We know that t is equal to 1 second, the positions when I'm writing down, and we know that velocity is to the right as well, it's positive. So there's a few ways to find the amplitude. That's not made clear in the problem. Let's just assume that we are in oscillating simple harmonic motion, since it is what's expected from this problem, though it should state that it doesn't. Anyways, so we're looking for amplitude. We know speed, we know velocity for at least a particular point in time. There's a few ways you can do this. You can use the cosine functions and start plugging in the initial conditions, and with that you'll get the amplitude and angular frequency while you're at it. But you can also then remember this formula between the speed and the amplitude, or well, the position, which is the speed is equal to plus or minus the angular frequency square root of, I have to double check this because it's the maximum displacement, the amplitude, minus the current position. So this is for a particular speed at some point in time, and we do have some initial conditions. We can plug in for speed and for position, and the only thing left would be if we knew omega, then we'd be able to find amplitude from this formula. We do know that omega is equal to the square root of the spring constant over m, so we know what this is, so we have no problem getting the omega. Now, the question is kind of nice, actually. If you look at the numbers, you get the square root of 400, which is just 20. In this case, would be rads per second. Moving on, the formula from here, then we can solve for amplitude. We can rearrange it, and via the algebra, what you end up getting is that the amplitude is equal to the square root of speed over omega squared plus x squared. And this formula kind of makes sense, right? Because the amplitude is max displacement. So at a particular point in time, when the speed is high, that means you're close to equilibrium, which makes x is small. But when x is really big, you're far from equilibrium, v is small. So these two terms in the equation balance each other, as they should, since the amplitude is constant. So at this point then, we'll plug in the initial conditions, what the speed is at 1 second and what the position is at 1 second. And from there, we can calculate the amplitude. So we have 4.33 squared divided by 20 plus x squared being 0.125 squared. And then that's all square rooted. So do the job of putting everything in the square root. So again, this is asking for the amplitude. So even though there's a bit of algebra, by this point we already solved the problem. We just have to follow through and plug in the numbers. And also, if you look at the units, right, you have speed over angular frequency. This whole term gives you meters squared. This is the second term. Square root of that, and you get units of meters, which is what you expect for the frequency. So once you complete this equation, you get about 0.25 meters. And that solves part A. So part B, in this case, asks for the period of oscillations. Thankfully, we know the angular frequency, and we know that there's a relationship between the two. So for part B, what I would do is just use the relationship between angular frequency and period. You recall the period is the reciprocal of the frequency. Frequency is related to angular frequency. Actually, that's the other way around. You know, we don't, like Bob Ross says, we don't make mistakes, just happy little accidents. Okay, so the relationship between period and angular frequency is 2 pi over omega. And the angular frequency being 20 rad, then the period should be pi over 10 seconds. So pretty fast. All right. The last question asks us to find the position and velocity at t is equal to 0. Now, this part of the problem, you've already been given some initial conditions, and now you're trying to find conditions at some other time. This last two parts, C and D, are sort of like an extra challenge and not something that you'd see on a test, a midterm, or an exam. But they're worth figuring out for the practice of it. So what the question is asking is, what's the position of the block at t is equal to 0, and what's the velocity of the block when t is equal to 0? So both parts essentially ask you to fill out the formula for position and velocity of a simple harmonic oscillator so that you can plug it in at time is equal to 0. The general formula, right, we can always write it with the general form, a cos omega t, and then there's some phase factor here. And then the speed being the derivative of the position formula. Gets us negative omega a cos omega t plus 5. So we want to find position, the actual initial position, t is equal to 0. We already know the amplitude, but we don't know the phase factor. So we know everything in the formula. We know omega a and not the phase factor. But we do have some initial conditions for t is equal to 1. So we know that at t is equal to 1, we'll have a position of 0.125. If that's true, then the formula at t is equal to 1 looks like this. We have a cos, that's the amplitude a, being a value of 0.25 times cos, and then omega t. So omega is 20, and this is at t is equal to 1 second, so we should have a 20 here, plus the phase factor 5. So the only unknown is the phase factor. We're going to solve for that, and you have to divide then 0.125 by 0.25 and then take the inverse cos function. So you're left with what's inside the cos function, which is 20 plus 5 is equal to the inverse cos of 0.125 divided by 0.25. And what this will get you is, if you plug this into your calculator, you'll get two solutions, though your calculator will only show you one. You will get 30 degrees, but there's another solution that satisfies the ratio, which is on the other side of the x-axis. So once you plug this into your calculator, what the calculator is probably going to tell you is going to give you 30 degrees. But a valid answer is minus 30 degrees, which is the same as 330 degrees. The one you go with, in this case, is the... Actually, I'm realizing now that I used the... I wrote the velocity formula here wrong. I wrote sine instead of cos. When you derive cos, you get a negative sine function. So the velocity formula should read sine here. Okay, so there's two angles. They're valid, 30 or minus 30, and whichever one you plug into your cos function, you'll get it'll work. But for the sine function, right, the velocity function has a sine function. But the question tells us that initially we're told that the speed is positive from t equals 0 onwards. So that means that our speed function, right, or velocity function, 0.25 negative 0.25 times 20 sine 20t plus 5, this whole thing, this whole term here is positive. So there's a negative sign at the front though, which means that our phase factor needs to make the sine term negative. So that with the negative sign at the front and the sign being negative, the overall result, the overall measurement of the velocity will be positive. So for sine to be negative, we go with the angle that's minus 30, or same 330. So to keep the number small, just choose the phase factor to be so to keep the number small, in this case, we'll go with a solution of minus 30. But because it wasn't just a phase factor on the left side above, the phase factor is actually minus 30 degrees minus 20. So now we have the full formula for the position function of time. And with that, then we can essentially plug everything in to get what the formula is at t is equal to 0. The only thing though is that we can't actually have 30 degrees in the formula because it's set up to work with radians. So we actually need to turn this to radians, which would be 5 pi over 6 and the -20 is still here. So what you should end up getting is a value of about oh sorry, hang on, 330 is not 5 pi over 6, it's actually should be about 11 pi over 6. So 11 pi over 6 is just minus 30 degrees, properly converted to radians. So, anyways, if you plug everything in, your displacement should be about negative 0.15. And if you do the same thing for your velocity for part B, you plug everything in and your answer should be equal to 4.25 meters per second. So again, these last two parts are a bit of a stretch, but they're not something you have to know for not something you'll have to do in the midterm. Anyways, last question for now is we have a block that undergoes simple harmonic motion. We know the amplitude oscillations, and we know at some moment the block is at this position here. And what is the ratio of kinetic energy to potential energy? So that's the first question, and then the second question talks about the energies being the same. Let's start with the first part. We have a block undergoing simple harmonic motion, so probably it's kind of spring block system, and we know that its equilibrium's over here. Right now, we're told it's at a point of 0.25 meters to the right since it's positive, and we know the equilibrium position is at here, marking the amplitude of a half meter. I don't like drawing graphs, it helps, doesn't take much. It's easier to sort of conceptualize what's happening in the problem if you have a visual to go with it. What is the ratio of kinetic energy to potential energy? The question asks. Well, first of all, what's the kinetic energy for a block? It's 1/2 mv squared, and the potential energy for the spring block system is 1/2 kx squared. So, given that you know the you know these two, you also know that the total energy is the sum of the two, and it always ends up adding up to 1/2 k a squared. So, what we can notice though is that the kinetic energy, right, at this particular position, x is equal to 0.25, but that's half the amplitude, right? So we can write this position then as being at half the amplitude, right? Because the amplitude's half meter, I wanted a quarter meter. So, but then if we kind of keep carrying that, then we can square this term. We'll have 1/2 k a squared over 4. We can keep the 4 outside. I'll have 1 over 4, 1/2 k a squared. And that is actually what the total energy is by definition. There's just a factor of a quarter in front. So when the block is at a position of 0.25 meters, the potential energy is 1/4 of the total energy. We also know that total energy at any point it adds up to the kinetic energy and the potential energy. And then we know that at the position of x being a quarter of a meter to the right, we know that the potential energy is a quarter of the total energy. So We still don't know what the kinetic energy is, but the we still know that the potential energy is a quarter of the total energy. And another way to think about this then is that the we can think about this another way though, that that 4 times the potential energy gives you the total energy. So if we go back to this formula, we can write the total energy as 4 times the potential energy, and that has to be, equal to the sum of the total and potential energy, which means that if you rearrange this, you get 3UE is equal to KE, and so the ratio between kinetic and potential energy is equal to 3. So that's it for part A. Part B asks about a point where the kinetic energy of the block is the same as the potential energy of the block, and it wants to know what displacement does this occur. So that is asking basically to just go with what it says, right? If we don't know what to do, if we're lost, we'll just listen to the question and just try to write down what the question tells us, but in math, right? Take the facts from the question, write them down. We're told that the kinetic energy of the block is the same as the potential energy. So, and we're looking for a displacement. So in part B, we're looking for some displacement, and the information given to us is that the potential energy is equal to the kinetic energy at this point. Well, if we're lost, we can go back to the formulas we worked on. We still know that the total energy is equal to the sum of the two. But we know that in this case, at this displacement, the kinetic energy is equal to the potential energy. So total energy is actually equal to 2 times the potential energy. That's kind of neat because we know that the potential energy, we know exactly what that is based on the amplitude, which is told to us, which we know what the amplitude is, and we know that potential energy is 1/2 k x squared, and this is the position we're looking for. So we found a way then to calculate the position x, and you might still see that we have a spring constant k, but it's on both sides of the formula, so it cancels out. So we have a squared divided by 2. We have it equal to x squared. So if you plug in your amplitude of 0.5 meters and well, square that divided by 2, but then you get square root again. So basically, you're actually calculating a over square root of 2. That's equal to 0.5 that was square root of 2. So in your calculator, that should get you a displacement of about 0.35 meters. So a bit of a different type of question, but it's good to think about, when you talk about energy, to go back to what you know about kinetic and potential energy and try to find a way to get to what the question's asking you based on what the question's giving you. Anyways, next time I'll do some these questions on waves, and we'll see where that takes us.